Welcome to this explainer. I am so thrilled you're here today because we are diving straight into the absolute cutting edge of aerospace engineering. We're going to break down the anatomy of a stealth drone and specifically look at the mind-bending science that manipulates sound, heat, and radio waves to make a modern flying machine basically invisible.
You know, for decades, we thought surviving in the air just meant flying higher and faster than the other guy. Well, high altitude and pure speed, they simply don't cut it anymore against modern interconnected detection arrays. We have officially entered an era where survival requires a multi-dimensional stealth battle.
So, that brings us to the ultimate, incredibly complex problem. How exactly do you hide a machine that screams as it cuts through the air, burns fuel at hundreds of degrees, and is constantly broadcasting electronic signals? How do engineers cloak a drone across three entirely different spectrums of physics all at the same time?
Well, we're going to look at this through three main pillars today: acoustic stealth, infrared stealth, and electromagnetic shielding.
Let's jump right into Pillar 1, acoustic stealth, or silencing the rotors.
What's really wild here is that engineers are literally taking a page from nature, using biomimicry in low Reynolds number aerodynamics. By combining multi-blade, low RPM configurations with swept tips in a double-slot, double-depth or DSDD design inspired by the silent flight of owls, they actually physically shatter those large, noisy air vortices. So instead of producing a loud, low-frequency chop that travels for miles, they convert all that energy into a high-frequency hiss that the atmosphere just easily absorbs before it ever reaches the ground.
But hey, engineering is always a game of give and take, right? Sure, you could slap on an extreme multi-tooth geometry on the blade and drop the noise by an impressive 8 to 10 decibels, but the power penalty for doing that is massive. It absolutely tanks your aerodynamic efficiency by over 15%. That drastically reduces your flight time and basically ruins the whole mission profile.
So engineers had to find the sweet spot, and that crucial target is a magic number, 7.2 decibels. By placing that DSD geometry precisely at 95% of the blade's radius, they achieved a 7.2 decibel noise reduction. To put that into perspective, that essentially halves the perceived volume to human ears. And they did it for a tiny, almost negligible 3.96% power penalty. It's a total no-brainer and absolutely the optimal choice for acoustic evasion.
Quick side note on what not to do before we move on. You might think adding traditional winglet proplets, like those little upturned tips you see on commercial airliners, would boost efficiency. Actually, scratch that. Tests prove they increase a drone's noise by 1 to 2 decibels. Even worse, they increase what's called psychoacoustic annoyance, which basically means they make the pitch much more irritating and noticeable to anyone listening on the ground. Definitely something to avoid.
Moving right along to Pillar 2, infrared stealth, beating the heat.
Now, a super common misconception is that you can just wrap a drone's hot parts in a bunch of heavy thermal insulation. But you really can't do that. It creates this thing called a heat accumulation trap. If you heavily insulate the drone, the internal heat from the engine and electronics just builds up, like a pressure cooker with nowhere to go. Eventually, it hits critical mass, literally cooks the internal systems, and flashes a massive, catastrophic thermal signature right through the hull.
The ingenious workaround for this is a WSTR coating. That stands for Wavelength Selective Thermal Regulator, paired with a specialized low-E or low-emissivity paint. Think of this metamaterial layer almost like a highly advanced one-way mirror for heat. In the specific atmospheric windows where enemy sensors are actively scanning, the low-E coating traps the heat so it stays invisible. But it's engineered to have high emission in atmospheric blind spots, specifically that 5 to 8 micrometer range where natural water vapor and carbon dioxide absorb the radiation. It literally dumps the waste heat into spectrums the enemy can't even see through.
And the results of this selective radiation cooling are just staggering. By venting this waste heat into the atmosphere's natural absorption bands, this coating can drop the drone's outer surface temperature by over 72 degrees Celsius. And that's even when the drone is tearing through the sky at Mach 2.2 and generating massive aerodynamic friction.
So what about the exhaust plume itself? Well, the drone uses an active 3-step process to mask it. First, it actively sucks in freezing cold bypass air from the outside. Second, it aggressively mixes that cold air with the high-temp engine exhaust inside a curved S-shaped duct. That curve is crucial because it physically hides the glowing hot engine core from being seen from behind. Finally, it expels this cooled-down mixture through a multi-layer ceramic nozzle made of carbon and silicon carbide, which dissipates the heat signature almost instantly.
Okay, bringing us to Pillar 3, EMI shielding, or cloaking the signals.
Because let's face it, even if a drone is dead quiet and ice cold, the raw processing power required to fly it generates stray radio frequencies. To stop the internal processors from broadcasting a huge electromagnetic footprint, engineers rely on a strict trinity: precise star-ground bus wiring to eliminate ground loops, advanced semiconductors, and complete 360-degree Faraday cage protection. That means utilizing specific stator conductive sealing and conductive elastomers to lock down every single microscopic gap.
Upgrading the drone's brain heavily relies on ditching old-school traditional silicon. When engineers step up to wide-band gap semiconductors, specifically gallium nitride or silicon carbide, the whole game changes. It allows for incredibly fast electrical switching at over 100 kHz. This shrinks the size of the electronic speed controllers by 45% while hitting an unbelievable 98% efficiency, which drastically cuts down on both the thermal waste and the radio noise they spit out.
And just to be absolutely bulletproof, every single circuit board is then sealed in a MIL I46058C conformal coating. We're talking about a microscopic military-grade polymer that's just 50 to 75 micrometers thick. It provides absolute electrical insulation, stopping stray short circuits and blocking electrical noise from leaking out, even if that drone is flying through corrosive salt spray or highly conductive desert dust.
Let's put it all together in our final section, synthesis. The symphony of invisibility.
Because true stealth isn't just one neat trick, right? It's a symphony of all three of these pillars working simultaneously within a single physical space. Just look at the tail section alone. You've got acoustic suppression on the customized propellers, the infrared S-duct exhaust masking the heat, and conductive elastomers sealing the electronics. Every single system works in absolute unison to keep this machine virtually imperceptible to the enemy.
Which kind of leaves us with a wild thought to wrap up this explainer. As detection sensors on the ground inevitably get better and radars become even more sensitive, will this incredible physical cloaking actually be enough? Or is dynamic AI-driven cognitive evasion, where the drone actively thinks, maneuvers, and adapts to threats in real time, the true future of invisibility? I will definitely leave you to ponder that one. Thank you so much for joining me for this explainer, and keep questioning what you see, or I guess, what you don't see.